The Compton effect is a phenomenon in which a photon, a quantum of light, collides with a free electron and transfers some of its energy to it. As a result, the photon's wavelength increases and its frequency decreases. This change in wavelength is called the Compton shift and depends only on the angle of scattering. The Compton effect demonstrates that light has both wave and particle properties, and it can be explained using quantum mechanics and special relativity 12. The Compton effect was discovered by Arthur Holly Compton in 1923, who won the Nobel Prize in Physics in 1927 for his work. He used X-rays to bombard a graphite target and measured the energy of the scattered photons using a crystal and an ionization chamber. He found that the scattered photons had less energy than the incident photons, and that the energy loss was greater for larger scattering angles. He also found that the energy loss was independent of the intensity of the X-rays, which contradicted the classical theory of light as a wave. 12. To explain his experimental results, Compton assumed that the X-ray photon behaves like a particle with energy E equals h and momentum P equals h/c, where h is Planck's constant, nu is the frequency, and c is the speed of light. He also assumed that the electron is initially at rest and obeys the laws of special relativity. He then applied the conservation of energy and momentum to the collision between the photon and the electron, and derived the following formula for the Compton shift: equals lambda equals mg 1 cos, where lambda and lambda are the wavelengths of the incident and scattered photons, respectively. M_e is the mass of the electron, and theta is the angle of scattering. This formula agrees well with the experimental data and shows that the Compton shift is proportional to the wavelength of the incident photon and the sine of half the scattering angle. 12. The Compton effect is important for understanding the interaction of high-energy electromagnetic radiation with matter. It is also a key evidence for the quantum nature of light and the dual wave-particle behavior of photons and electrons. Compton scattering and Rayleigh scattering are two types of phenomena that describe how light interacts with matter. The main difference between them is the size of the scattering particles and the energy of the photons. 12. Compton scattering occurs when a high-energy photon, such as an X-ray, collides with a free or loosely bound electron and transfers some of its energy to it. This causes the photon to lose energy and increase its wavelength, which is called the Compton shift. The amount of the shift depends only on the angle of scattering and not on the material or the intensity of the light. Compton scattering demonstrates the particle nature of light and the relativistic effects of electrons. 12. Rayleigh scattering occurs when a low-energy photon, such as visible light, interacts with a small particle, such as an atom or a molecule, whose size is much smaller than the wavelength of the light. The photon does not lose energy, but changes its direction randomly. The amount of scattering depends on the polarizability of the particle and the inverse fourth power of the wavelength of the light. Rayleigh scattering is responsible for the blue color of the sky and the red color of the sunset. The photoelectric effect is the phenomenon of electrons being emitted from a material when it absorbs electromagnetic radiation, such as light. The energy of the emitted electrons depends on the frequency of the radiation, not on its intensity. This shows that light behaves like a particle, called a photon, rather than a wave. The photoelectric effect was discovered by Hertz in 1887 and explained by Einstein in 1905–123. To explain the photoelectric effect in more detail, let us consider a metal surface that is exposed to light of a certain frequency. According to the classical wave theory of light, the light should transfer its energy to the electrons in the metal gradually, and the electrons should be emitted when they accumulate enough energy to overcome the attraction of the metal. However, this is not what happens in reality. Instead, the following observations are made: no electrons are emitted if the frequency of the light is below a certain threshold, regardless of the intensity or duration of the light. This means that there is a minimum amount of energy required for an electron to escape the metal, which is called the work function of the metal. Electrons are emitted instantly as soon as the light hits the metal, even if the light is very dim. This means that the energy transfer from the light to the electrons is not gradual, but instantaneous. The kinetic energy of the emitted electrons increases linearly with the frequency of the light, and does not depend on the intensity of the light. This means that the energy of the light is proportional to its frequency, and not to its amplitude. These observations can be explained by assuming that light consists of discrete packets of energy, called photons, whose energy is given by the formula E equals h, where h is Planck's constant and nu is the frequency of the light. When a photon hits an electron in the metal, it transfers all its energy to the electron in a single collision. If the photon energy is less than the work function of the metal, the electron cannot escape the metal and the photon is reflected or absorbed. If the photon energy is equal to or greater than the work function of the metal, the electron can escape the metal and the photon is absorbed. the excess energy of the photon becomes the kinetic energy of the electron, which is given by the formula K equals hW, where W is the work function of the metal. This formula is known as the Einstein equation for the photoelectric effect. It shows that the kinetic energy of the electron depends only on the frequency of the light and the work function of the metal, and not on the intensity of the light. The photoelectric effect provides strong evidence for the quantum nature of light and the dual wave particle behavior of photons and electrons. It also has many applications in physics, materials science, astrophysics, and technology, such as photodetectors, photovoltaic cells, and photoelectron spectroscopy. X-ray crystallography is a technique that uses X-rays to determine the atomic and molecular structure of a crystal. A crystal is a solid material whose atoms are arranged in a regular, repeating pattern. When a beam of X-rays hits a crystal, it is scattered in different directions by the atoms. By measuring the angles and intensities of the scattered X-rays, a three-dimensional picture of the electron density within the crystal can be obtained. From this, the positions and bonds of the atoms can be inferred. One X-ray crystallography was developed in the early 20th century by scientists such as Max von Laue, William Henry Bragg, William Lawrence Bragg, and Arthur Compton. It has been used to study the structure and properties of many materials, such as metals, minerals, semiconductors, and biological molecules. For example, X-ray crystallography revealed the double helix structure of DNA, the molecular basis of life. 12 To perform X-ray crystallography, a single crystal of the material of interest is placed in an X-ray beam and rotated. A detector records the diffraction pattern of the X-rays as they are scattered by the crystal. The diffraction pattern is a series of spots that represent the interference of the X-rays. The position and intensity of each spot depend on the shape and size of the crystal, the wavelength and angle of the X-rays, and the arrangement and type of atoms in the crystal. 13 The diffraction pattern contains information about the structure of the crystal, but it is not easy to interpret. To solve the structure, a mathematical process called Fourier transform is used to convert the diffraction pattern into an electron density map. The electron density map shows the distribution of electrons in the crystal, which reflects the positions of the atoms. However, the electron density map is not unique, and there may be more than one possible structure that fits the data. To resolve this ambiguity, additional information, such as the chemical composition, symmetry, and bond lengths of the material, is needed. 13 X-ray crystallography is a powerful and widely used method for determining the structure of matter at the atomic level. It can reveal the shape, size, and function of molecules, as well as their interactions and transformations. It can also help to design new materials and drugs with desired properties and functions. The Compton effect and the photoelectric effect are two phenomena that show how light interacts with matter. Both effects demonstrate the particle nature of light, but they have different conditions and outcomes. Here are some of the main differences between them. The Compton effect occurs when a high-energy photon, such as an X-ray, collides with a free or loosely bound electron and transfers some of its energy to it. The photon loses energy and increases its wavelength, which is called the Compton shift. The electron gains energy and recoils. The photon and the electron are both scattered in different directions. 12. The photoelectric effect occurs when a low-energy photon, such as visible light, is absorbed by a bound electron in a material and ejects it. The photon delivers its entire energy to the electron, which overcomes the attraction of the material and escapes. The photon disappears and the electron becomes a photoelectron. The kinetic energy of the photoelectron depends on the frequency of the photon and the work function of the material. 1, 2, 3. The Compton effect is a mid-energy phenomenon that can happen with any material, as long as the photon energy is greater than the electron binding energy. The photoelectric effect is a low-energy phenomenon that depends on the material, as there is a minimum frequency, or threshold frequency, of the photon required to eject an electron. 12. The Compton effect shows the conservation of energy and momentum in the collision between the photon and the electron. The photoelectric effect shows the quantization of energy in the absorption of the photon by the electron. 12. The Compton effect reveals the relativistic effects of electrons, as their mass and velocity change with the photon energy. The photoelectric effect reveals the quantum effects of photons, as their energy and frequency are proportional. That uses a beam of electrons to create images of the surface of a sample. The electrons interact with the atoms in the sample and produce different signals that reveal information about the shape, texture, and composition of the sample. 1 To understand how a SEM works, let's look at the main components and steps involved. The electron source generates a stream of electrons that are accelerated by a high voltage. The electron source can be either a thermionic emitter, which heats a metal filament to release electrons, or a field emitter, which uses a sharp metal tip to extract electrons by a strong electric field. 12. The electron beam is focused and scanned by a series of electromagnetic lenses and coils. The lenses control the diameter and convergence of the beam, while the coils deflect the beam in a raster pattern over the sample. The scanning speed and area can be adjusted to change the magnification and resolution of the image. 12. The sample is mounted on a stage that can be moved in 3 dimensions to adjust the position and orientation of the sample. The sample is usually coated with a thin layer of metal to make it conductive and prevent the accumulation of electric charge. The sample chamber is kept under a vacuum to prevent the interference of air molecules with the electron beam. 12. The detector collects the signals that are generated by the electron-sample interaction. There are different types of signals, such as secondary electrons, backscattered electrons, characteristic X-rays, and Auger electrons, that provide different information about the sample. For example, secondary electrons are emitted by the atoms near the surface of the sample and are sensitive to the topography and morphology of the sample. Backscattered electrons are reflected by the atoms in the sample and are sensitive to the atomic number and composition of the sample. Characteristic X-rays are emitted by the atoms in the sample when they are excited by the electron beam and are sensitive to the elemental and chemical analysis of the sample. Auger electrons are emitted by the atoms in the sample when they relax from an excited state and are sensitive to the surface chemistry and bonding of the sample. 1, 2, 3. The image is formed by processing the signals from the detector and displaying them on a monitor. The brightness of each pixel corresponds to the intensity of the signal from a specific point on the sample. The image can be enhanced by adjusting the contrast, brightness, and color of the pixels. The image can also be analyzed by measuring the size, shape, and distribution of the features on the sample. That was all. Goodbye.